All right, good. So I'm very excited about this.
Me
I
too.
think I think this is gonna be so much fun to work on. And I just got a note back from Dave, the editor of the one who asked me about it. And when I said, "Hey, here's my idea, and is it okay if I co-write it with Logan?" And he said, "Great." So
Yes.
and
Okay,
we have
cool.
official approval. Let's see. Let me find it just to. Uh,
In writing.
yes. Well, and in fact, he said, I need to reply. I haven't yet. So he says, Todd, thanks for your review because I sent a review of another
Oh,
paper.
nice.
I'm glad you suggested the references, blah, blah, blah. That's not relevant. Okay, he says that Springer chapter sounds great. And I sent him the same abstract I sent you. I'm going to modify it a little bit
Hmm.
because I'm thinking about the term Big Bang and how ambiguous that is. Like that's going to be
Right.
one of our discussion points. Anyway, so I added a little thing that says, Big Bang in quotes and says
Hmm.
extrapolated t equals zero time,
Hmm.
something, something
Like
to explore.
singularity
Like,
kind
yeah, like what do we, you exactly. Like, in fact, that's going to be, should you choose to accept it, that's going to be your first assignment is I
of.
have start with a question for Logan. What do we mean by the quote age of the universe? How would you define it and calculate it? So,
Ooh, okay,
so
cool.
you can be pondering that. We'll come back to it. Anyway, but
Cool.
he says, yeah, he says, thanks for collaborating with Logan. That Springer chapter sounds great. I wanted to note that Leonid Grinnin, who's one of the other collaborators on this, mentioned the possibility of including a paper that he wrote in 2018 called Was There a Big Bang, which explores
Mm,
inflation and sort of similar questions. He really does not deal with motivation of the inflation theory, tests, nor problems with current theories. Given that he has other contributions to the volume, it may be worth considering whether we might instead prioritize your updated piece. So I'm very open to your thoughts. So anyway, so all of that is just to say, I I read Leonid's paper, and I don't think we're going to duplicate anything. So I'll make some arguments about whether that should be included or not or whatever. But I think it'll be neat. We can have sort of a counterpoint
nice.
about it too. So so yes. So I mean, so let me tell you my thoughts about the idea of it because it's very open-ended and it could become something totally different if you want.
Mhm.
But
Let me get my,
what's that?
oh, I'm gonna get my iPad.
Okay, and in a minute I'll share my iPad so that we
Okay,
can
cool.
make notes and stuff. But here's sort of my thought for you and me and your education and my education and the big history community's education and everything. So I have written I got really excited about this. So I currently have a 6-page document plus a bunch of,
Yes.
plus like I realize I have a folder of like 40 references now. Somehow, you just get in the mode where you're like, oh, I should look up this and I should look up this. And I copied
Uh-huh,
all the
uh-huh.
references to it. And then I realized, well, that's a lot. Um, and then I have notes on the iPad. So, I mean, there are lots of things we could do, but what I'm roughly thinking would be really useful for the community and for you as you start off on grad school is there's so much. Actually, I think it comes back to the philosophy of our AJP paper of don't lose the thread of your own intuition.
Hmm. Hmm.
It is like I think the next step of where it sounds to me, so correct me if you don't agree with this, but it
Hmm.
sounds to me like what you're wanting to work on and stuff, delving into how people think about the early universe would be a good step for
Yes.
you,
No,
right?
yep.
And
Yep.
so,
Very
like, just to
much
give you an
so.
example, remember the part three math notes from Dan Bauman that
Hmm. Hmm.
that you alerted me to from your CERN lecture. So I've been reading that and going back to
Okay.
my notes from when I
Okay.
was in the part three math
Uh-huh.
stuff at Cambridge. And it's funny because my questions have not been answered yet. So this is 30 years later, and my questions remain relevant. So that was fun. I
Wow.
literally pulled out my notes from, oh, here's Martin Rees's lecture, and here's
Uh-huh.
So in the conversations I had with him about these things, and a lot of these things are still unresolved, right? I mean, um, so what I would like to do is try to write something that cleanly distinguishes what do we know solidly about the early universe, what
Hmm.
needs to be explained, so what do we solidly know from extrapolating back?
Hmm.
What are the questions that need to be explained?
Hmm.
And then what are some possible ways to explain them,
Hmm.
but not entangling those quite so much as they have understandably gotten to be in just the way a research community unfolds, right? That um, probably since the 1980s-ish, inflation has gotten very entangled with what early universe cosmology is and how we explain these problems like the flatness problem and the horizon problem and things like that.
Right.
And there's there are unconscious assumptions about what an explanation means and what kind of explanation counts and that
Hmm.
and there are I mean inflation it could really be that there was a moment a series of moments in the early universe when inflation happened that totally could be,
Hmm.
but it's not clear that it did happen.
Yeah.
And I think that needs to be highlighted.
Uh-huh.
And the reasons for proposing that it did happen are to explain certain problems that, I wouldn't even say problems, to explain certain facts
Hmm.
about our current universe that
Hmm.
might have other explanations. And it might even be worth, thinking of some of the things we've talked about the relationship between the observer and the description or the observed. I know
Hmm.
there might be other explanations, and I think it's really important to tease out what needs to be explained from a sort of an automatic assumption about what the explanation looks like because inflation has some real problems too, and there are some more and more vocal people in the community. There's a good article by Paul Steinhardt about alternatives to inflation. um, so it just I'm not I don't want our piece, or at least I would, unless you disagree or we come to a new conclusion, I don't really want to
Hmm.
argue against inflation. I just don't want to assume it, I think,
Yeah, no, I
right?
agree.
So I'd like to do something and what I'm imagining for you then is that you would get to the end of this project and head into grad school with just like a really clear roadmap in your mind about these are the things we know, these are the things that people tend to assume, here's why they assume them,
Hmm.
here's some other possibilities. You know what I mean? Just so that you kind
Yeah.
of have a sense of what's solid, what's not solid, what do we mean by the different terms, so that you can then kind of have as unbiased as possible a framework to go into. Like now when people start telling you stuff based on their own biases, and you have some sort of way to ask good questions and to decide what you think about it. And you know what I mean? That you're not, that you can follow your own intuition, that you're not just having to regurgitate because you don't know what to question
Yeah,
or
like
what the
people can
reasons.
say things and then I can kind of like compare them to the roadmap that I have
Yeah,
established already and like
exactly.
place them in it or find things that might rebuttal them or just kind of be able to navigate the world.
Exactly. And you can ask probing questions about, well,
Hmm.
okay, why are you assuming that? So like just as a for example, I'm reading about the history of inflation, and where did I put those notes?
History.
Like the history of like how did people come to the idea of inflation? What were they trying to explain? What were the discussions that happened? Um, and there it is. Um, So just to give you an example of the thinking, right? So I'm reading along. Here's a quote from so Paul Steinhardt has a paper called The Inflation Debate in
Mm,
Scientific American from April 2011. So it's like what, 14, 15 years old. Um, and he tells the history of inflation, and he has a line in there where he says that we observe that the primordial universe, must have been very uniform and flat, geometrically
mhm,
flat.
mhm,
And he says, a priori, these conditions seemed unlikely. Um, and so then I put in my notes, I asked the question, well, that's fair, but on what basis do they seem unlikely, right? And
mhm,
I was sort of asking myself, it boils down to, you know, we have to remind ourselves the universe has apparently just come into being. And I'm making claims about what I think is likely or unlikely for a universe that has just come into being, like what properties
mhm.
it should have. And I realize I don't really have any business claiming what I think is a priori likely or like why would I does that make sense? Why would I expect it to be not uniform?
Yeah.
That's
Like what biases or assumptions are we making to
yeah.
like
Like
assume that it had a certain state before everything
yeah.
when we have no idea what it.
I mean, we have no idea about anything at some point. I mean, and it's, and of course, in science, we have to try to push our assumptions and so on, and so it's reasonable to do. But I just, the sort of basic argument boils down to something like, if I if I walk into a restaurant, if you're in New York City and you have seen, obviously, there are lots of people dressed very differently.
Mhm.
You walk into a restaurant and everybody is wearing identical Pacific University t-shirts.
Uh,
That needs to be explained, right?
yeah,
Clearly.
yeah.
And the explanation is probably that all those people communicated beforehand somehow, because you know that at random, if they all just showed up at a restaurant, they would probably be wearing a wide variety of different things. So that's the sort of argument that
Right.
led to inflation,
Well,
is that in the very early universe, the conditions were sort of the same everywhere in regions that had not had time to communicate. And so that seems to demand an explanation. But I'm just a little worried about it because I start thinking, well, the laws of physics are also the same everywhere. And I don't
right.
really know how those got to be the same. I mean, it's a different situation than a restaurant in New York City, right? It's the
Yeah.
beginning of the universe.
Yeah.
And so I don't know for sure what I mean by explaining what needs to be the same or not the same. So that's sort of just a
Mhm.
caveat that's kind of in my mind. Um,
I like that caveat.
right?
Yeah.
So so anyway, so those are the kinds of things. So what I'd like us to do in this paper, if this sounds okay, is basically just put some stakes in the ground about why we think what we think about the early universe, what seems pretty solid based on the evidence, what some open questions are, and what some possible explanations for those open questions might be. I think that would be a good paper.
Yeah,
I mean,
I really like that.
maybe we can come, we could have a reflections at the end and we could say what we think. But
Hmm.
I think it's probably better if we go into it not trying to argue for anything in particular, but sort of, except maybe to argue that people are too quick to jump to conclusions. And so we want to try to not do that and
Yeah,
just
it's
spell
like
out.
a paper that is giving people the tools to make their own opinions about what's
Yes.
going on in the early universe.
Right. And almost a review paper kind of about like
Yeah,
here's some
yeah.
possibilities, right? Like but
Hmm.
with a lot of emphasis on what needs to be explained without jumping to the explanations. So
Hmm.
so and the other thing, and you should correct me or steer me or whatever. I'm just trying to kind of think based on our previous conversations. But one of the things we talked about in our last conversation that I've been pondering a lot is your comments about how it feels, how easy it is to become passive and just
Hmm.
reading things and not sort
Hmm.
of doing your own calculations and doing your own. I mean, not, and I don't mean you by like singling you out. I think
Yeah,
that
like
we all do
royal,
this, but
royal you.
you're just talking about it, right?
Yeah.
I had this temptation as I was going through all this. I was like, oh, I should send this paper to Logan, and I should send this paper to Logan, and I should send this paper. And then I decided not to send you any papers
Uh-huh. Yeah, no, I was
because,
actually
go ahead.
like this afternoon I was at the cafe. I was like, all right, now I'm gonna get my brain into early universe mode. And I was like, I feel like Todd would have sent me papers by now.
That's funny.
So I just started kind of doing stuff on my own.
I
And
had
I was
many
like,
moments of
wait a
temptation and I reflected on it and I decided, I mean, and of course there are papers that will be useful for you to read for
Mhm.
sure. Including the Bauman. I think the Bauman lecture notes.
Right.
Um,
Yes.
he has both he has both lecture notes on cosmology in general, the ones
Hmm.
that you followed, and then he also has a specific set of lecture notes on inflation.
Oh,
And
nice.
I think both of those will be useful.
Hmm.
But I'm thinking of them more as like references to go back to anchor
Hmm.
ourselves, as opposed to like trying to follow along and recreate all of his calculations.
Right.
Um, because you'll probably get plenty of that next year, honestly, right? I'm sure you'll take a
Uh-huh.
cosmology or general relativity course and stuff. So what I thought I would try instead, in the spirit of what you were kind of talking about and asking for, is let's, because you have some background, right? You've looked at these notes. We've done your capstone, and remember we did all those Friedman equation calculations and
Yeah.
stuff like that, which both of us have
Uh-huh.
probably partly forgotten since then. But so, what if we try to basically do what the philosophy of that AJP paper advocates for, which
Hmm.
is let's let's identify some questions and then have you try to answer them with calculations yourself. And
Hmm.
it's like you can of course go look things up and you can ask me stuff and whatever. But so that the thread becomes your own intuition starting from
Hmm.
the question rather than replicating somebody else's intuition and argument. Does that make
Yeah.
sense? Does
Yeah,
that
I
sound
like that a
yeah.
lot.
So for example, my question for today is I'm sure you have heard, and I've thrown around the statement that the universe is 13.8 billion years old,
Hmm.
and what we call the quote Big Bang is the time zero of that 13.8 billion years ago. So my question for you is, what do we mean by the age of the universe, and how would you calculate that? Like if you had to get that 13.8 billion year number, what would you do to try to get a number?
Hmm.
Because and that 13.8 billion years is often referred to as the expansion age of the universe. Um, so that's my starting point is I should say, what do we mean by the expansion age of the universe? I guess I should have said. Um, and then how would you calculate it or how would you define it? So I was thinking, let's just sort of talk that through. And then I'm hoping that we can talk it through to the point where you feel like you could go away and do a calculation that would give an estimate.
Hmm. Well,
So yeah, thoughts?
yeah. So, I mean, I know that like the Big Bang is a singularity.
Okay, good.
And like when we were doing the like Friedman equation stuff, when we were trying to find the different kinds of rows, the different rows represented different ages of the universe. because like the certain eras on the cosmic calendar.
Mm-hmm.
So there's probably a row in which it's so dense that it is a singularity.
Okay.
So we can probably then use that row. And I mean, the solutions that we found when we were doing those equations, those differential equations, the solutions were the scale factor as a function of time.
Uh-huh.
Um, and so we can probably get a time from whatever solution we get from the row that we choose to make it the singularity, which is perhaps the Big Bang.
Perfect. Nice
Yeah.
job. Nice job. Yeah,
Yes.
that's really good. That's hard to put together on the fly. So, yeah. So the singularity is basically R equals zero, right? Scale factor
Mm.
equals zero,
Oh, okay. Okay.
right?
Uh-huh.
So, I mean, it's like an extrapolated, like we sort of by convention we set R equal to one now. You could set it to be
Hmm.
whatever you want, I guess, depending on how you define other things. But um, like just like you said, right? The Friedman equation gives us a differential equation for R as a function of time,
Hmm.
right? And what we mean, the whole idea of the expanding universe and the Big Bang idea is that the universe is expanding, which means numerically that R is shrinking as you go back in time. And so you can solve that, you can integrate that equation, right? If you know what dRdt is,
Hmm.
if you have an equation for dRdt,
Hmm.
then you can integrate that equation. You can separate it and integrate the equation to get like integral from time now to some time that we're going to call zero
Hmm.
is from R now to R zero,
Hmm.
right? How long does it take to go? And actually, you don't need to, you can do any period, right? You basically ask, how long does it take? This is probably a better statement for me to make. If you have a differential equation for how R changes with time,
Hmm.
then you can pick any two times corresponding to any two R values,
Hmm.
and you can ask how much time elapsed between them. I didn't say that quite right. You can pick any two R values. That's a better way to say it.
Hmm.
You can pick any two R values and ask how much time elapsed between those two R values,
Okay.
right?
And I think I'm kind of confused on why, because I mean, I know the scale factor is like when, my example, like in my presentation with like good notes and the graph, right? And the like we would like highlight the graph and then we can stretch it and shrink it.
Yep.
Like that's the scale factor. And so like, and I guess then I understand like dr dt because
Yep.
it's kind of like how fast that shrinks or expands.
Yep.
But I don't think I quite understand what it means for like R equal zero or like R equal one and like what the significance of
Yeah,
those
yeah,
specific
gotcha.
numbers are and like what the numbers mean.
Gotcha. So that's probably, I mean, what you've done already conceptually is about as far certainly as I could go in my head, right? I mean, we
Mhm.
need to see some things written down in order to, right? So I'm assuming we'll we'll just so you can see my screen now, right?
Yeah.
You can see my iPad screen. So, this is going to become our friend,
Yes.
right? Um,
Favorite
Oh,
equation.
sweet. I did not know that it was set that way. So apparently I have a pointer,
Huh?
right? So could you see when I do this, you can see it and then it fades? Yeah, okay,
Yeah.
cool. Cool, cool.
Wait, can I
Um,
draw?
can you draw on it too? Yeah.
Can you see that?
Uh-huh. I see a
What?
cursor.
Oh, wait, but I drew a
I
line. Can
see
you see
like
the
a red
line?
line.
Oh, yeah, that's what I
Oh
did.
yeah, that's what we discovered last time, right? And it's not going to
Oh,
be,
yeah, I
it's just
think
on the
you're right.
screen. It's not going to be attached to my document, but that's all right. You can at least point to things.
Yeah. Oh, yeah, because I have. Wait. Oh, no, that's the color. Do I have a pointer too? Arrow, arrow?
Yeah, oh, that's cool. It's a little arrow that has your name on it. It points to things.
That's funny.
I like this. We should all have arrows with our names on them.
Oh.
Nice. That's
Sorry.
good. This is good.
Okay.
All right, so yeah, so right, so we've got the Friedman equation, right? Gives you that. So it's a differential equation.
Hmm.
So that doesn't have any start and end times. It just tells you, you know, dr dt,
Characterizes
right?
the evolution.
And it tells you slopes essentially, right? It tells
Mhm.
you that the slope of r versus t, but it doesn't tell you what r is as a function of t. And then we also have another variable which is rho. And so as you probably remember, you kind of said in your comments when you did your capstone, right? So we have these different cases depending on, let me move us out of the way. We have these different cases depending on, like if there's non-relativistic matter, then rho is proportional to r to the minus 3, right? Um, because um,
3D
volume,
world.
right?
Yeah.
Density is just mass over volume. We assume mass is fixed. This with the non-relativistic means, and if we have relativistic matter or radiation, which is usually what we think of like light, then it scales as r to the minus 4, and that's because not only do the density of the photons go down as it expands, but also they get redshifted, right? They get stretched, so they lose energy. Yeah.
Hmm.
So anyway, the point being, and in fact, I'm going to suggest that for our initial calculation, um, just so here's where we can anchor ourselves in observations, right? If we look right now, um, well, actually, right now it's vacuum energy density dominated, which is its own weird puzzle. Thinking about that today, like why is the vacuum energy not zero? That's why the expansion is accelerating
With the dark
now
energy.
because there's dark energy, right?
Hmm.
Um, you know, it's a pretty deep particle physics mystery why that is very small, right? I mean, in terms of from a particle physics standpoint, the vacuum energy density is tiny, but it's not zero, and that matters. But anyway, but for most of the history of the universe, at least the current incarnation of the universe, right? It's been matter dominated, right? Because if you go, you have to go back to about what, a few 100,000 years after the time zero before radiation. Remember those charts of how because of this, because of their dependence on R, as R gets small, eventually radiation dominates,
Hmm.
right? Because at small r, this becomes big
Hmm.
faster than this becomes big,
Right.
right? If you just think of the graphs of, what r to the minus 3 looks like versus what r to the minus 4 looks like. R to the minus 3 is uh, less steep,
Right.
right? Like I guess I could actually draw it with a real pen, right? So um, if this is r, r to the minus 4 is going to be steeper. It's not quite right here, but something like this, right? This one is like r to the minus 3, and this one is like r to the minus 4. See what I mean?
Yeah.
So as r as r approaches 0, which obviously my red line is not good because it's going to have to do something weird to not hit the origin there. But you get what I mean, right? It
Uh-huh.
needs to. All right, here, let me fix that. It also needs to not hit the origin, but oh, that's not good.
It's a constant slope.
Yeah. It needs to not hit the origin, but it approaches the origins less steeply than the blue one, right?
Right.
So this is this is the equivalence point, and this happens at something like on the order of 10 to the fifth years, just observationally. If you look at what the radiation density is now and what the matter density is now, and then there's also, this is the vacuum
Interesting.
because it's constant, right?
Yeah.
It doesn't vary with R.
So the vacuum was equal
Well,
to
sorry, I didn't make
okay.
it right. Yeah, you're right. I should. It's got to be lower. Make it green. Yeah. So it's like down here, right? So there's some time that we have now entered when the vacuum energy starts to dominate,
I see.
right? And that's like nowish,
Hmm.
which is why
And
we see noticeable
because
vacuum energy.
the like because the vacuum energy is dominating, that is what's causing it to accelerate because it doesn't have the gravitational influence to balance it because the matter density is lower.
Correct. Correct. Right. Yeah.
Okay,
Because this is, if you look at you know, look at the Friedman equation here, right, with rho, and rho technically equals rho vacuum plus rho matter plus rho radiation. And those have different dependencies with R.
hmm,
And so in the early stage, you can basically, you remember when we talked about things like the radiation dominated era?
uh-huh,
What that basically means is that I can ignore these other two.
right,
Um, the radiation dominated era means that that's the only thing that counts here because it's much bigger than this and this.
okay,
But then once the matter radiation equivalence happens, then after that, then I basically need to treat it as mostly this.
right,
And then once the vacuum starts to dominate, then I treat it as mostly that. And then my differential equation is different, right?
mm,
Because my dependencies are different. And of course, I mean, in principle, especially if you're doing this numerically on a computer, what you really should do is you should just put everything in here and solve it.
mhm,
But as you know, it was hard enough mathematically to solve it just for one constituent. And so it's much easier to do the math if it's dominated by one or the other, which is why we're doing the calculations that way. Yeah.
yeah,
And, and what I was getting at for back to my question about what's the age of the universe, because this happened really early, um, that matter started to dominate. This amount of time is pretty small. in the overall scheme of things. So basically, if you want to estimate the age of the universe, you can just put in this for rho to do your calculation. See what I
Yeah.
mean?
Hmm.
So I think I tried to do that. I have all kinds of notes here. Yeah, right. So if I want to find the practice age, I'm just going to say, okay, well, let's just suppose that the universe is matter dominated always. And I'll go back and correct that if it's a bad assumption later. But
Hmm.
and then and then that means that I can put my Friedman equation in here, but I can replace my unknown rho with some rho naught, which is the current density, times r to the minus 3. Right. And now, and then I just made a kappa here because I got tired of writing 8 thirds pi g rho over and over again. You can do this however you want. But right. So to answer, this is my long-winded way of answering your question, is that I get to the point where I can write this as an integral, right? And
Hmm.
the key dependencies here are I have basically on one, whoops,
No, you don't.
on one side, yeah, I made an eraser. On one side, I have the scale factor to the 1/2 times the, dr equals some constant stuff times just dt. And so then I can integrate that. If I just arbitrarily choose, I'm going to say, I'm going to call when r was 0, I'm going to call that t0,
Hmm.
right? And I mean, I think that's the key. Like, that's what we mean by
Or
the
is
time zero Big Bang is if I extrapolate back, I have no business assuming that the universe is going to continue to be matter dominated all the way back to a scale factor of 0.
uh-huh.
But I can make a model that assumes that, and then I'll figure out any problems later, right? So if
Hmm.
that was the case, then back to your point, then it makes sense to call that singularity the time zero, because that's just the extrapolated back when everything that I see today was on top of each other. That's what I'm going to call my beginning point. I wouldn't
Uh,
have to, but that's a reasonable thing to call it, right?
yeah.
And so then I can integrate, to make this match some R and some T that I want to start from. Basically, if I want to ask how old was the universe when R was some value, then I just pick a value of R, and I'm being a little sloppy. Chris Gunther would probably not be happy, so I'm going to call this dt prime, and that's going to be r prime and dr prime, right? Because
Hmm.
I want my r and time variables there to be, or actually maybe a better way to do it. Let me do this. Um, I'll just call this t now and r now.
Okay, yeah.
Yeah. So I can integrate this and I'm going to get an equation for, these are the famous, remember, I think we derived this during your capstone that,
Hmm.
except we only cared about, matter dominated R is proportional to T to the 2/3 and
Hmm.
radiation dominated, remember it was T to the 1/2.
Hmm.
Um, but uh, I think I have not followed this through yet, so this is part of your homework, right? I mean, I've done this homework problem many years ago, but I haven't done it recently. So it's that once you have this equation, right, you can make this specific. You can
Hmm.
you can now say some r as a
T
function of t
or
is going to be a specific equation times the amount of time that's elapsed to the two-thirds.
Mhm.
And then if you want to know, you can solve that for t. I guess I put in zeros here.
Yeah, because like R, so R of t would equal zero because R equals zero is the scale factor at the time of the quote
The
unquote Big
beginning,
Bang.
right. And we've already included that. I already included that in order to do this.
Right. For the
So this
interval.
is really R now, which or
Yeah,
whatever you want to pick as your
yeah.
now. And we might as well just, I think, say, let's
One.
make that one.
Okay. And why is it one?
Um, it's because of how the co-moving distances are defined. So remember, somewhere in here, there's like the physical distance equals the scale factor times the co-moving distance, which is the coordinate distance, on in your um, general relativity kind of coordinates.
Uh-huh.
And so it's just a
Right.
choice of where to, the physical units are here. And so then your scale factor
Is
is
like
is
warping
defined
it.
to be one today because then today is the kind of, you know, standard of if something is, you know, uh, if something is 5 light years apart today, then that defines its it's like you've made a shell that you can enlarge or contract by the scale factor,
Uh-huh.
and then you've absorbed the dimensionless part into the scale factor and the physical part into the co-moving distance so that, so you can treat it as if everything stays the same in co-moving coordinates, and then you just at the end you multiply it by the scale factor to get, what it'll actually be like. So if something is 5 light years apart today, then when the scale factor was only a fifth of what it is today, then those things, if nothing else happened, would be only a fifth of the distance
Hmm.
away. But in both cases, the co-moving distance stays the same, and the scale factor just changes it.
Okay.
Yeah.
So like in the future, like
In the
pretty
future,
far
it'll
into
get
the
bigger than
future.
one.
Okay, cool.
Right. Right. But again, you can make as long as you make everything consistent, you can make your scale, all that matters is ratios of scale factors, not the sort of absolute scale factor.
Right.
Yeah.
Okay.
Um, and the Hubble constant. So we have units for, the H is defined as R dot over R,
Hmm.
and H now is equal to, of course, then R dot over R now. And that's what we can measure. And that's about 70 kilometers per second per megaparsec.
So if R now is one,
Then R dot now is 70 kilometers per.
okay.
Yeah, the units are weird.
Because I
Uh,
was gonna say like taking the
because R dot is,
derivative
yeah,
one is zero, but
right. R is dimensionless.
right.
So the fact that R is one now doesn't mean that R dot is anything in particular. You're right. I mean,
Yeah.
let's see. Because this, if I make the units reasonable, this has units of, this is going to be some number times 1/seconds if I make the units compatible, right? Megaparsecs are just another distance.
Hmm.
So if I if I convert megaparsecs into kilometers, I get units of 1/seconds, which is reasonable for r dot because it's a derivative of a dimensionless quantity scale factor per second. Make sense?
Wait, what, can you say that again? Derivative
Well,
of
the units of r dot are 1/seconds.
hmm right.
I guess that's all I was saying. Yeah.
Okay.
I know the units on all this stuff are weird, but um, anyway, so I think with that information, I think you can. This will give you. You can solve the if you put the things back in that I took out for this. You can you can use the Friedman equation to replace some of this stuff. It'll require a little detective work, but you can replace some of this stuff with known quantities like the Hubble constant, and this will actually give you a value for the age of the universe if you assume that it was matter dominated all the way back. So I think that is a really useful calculation to try to do yourself. Like, don't worry if you get stuck or can't do some piece of it, but you'll appreciate the whole flow of what we're doing if you try to start from scratch with the Friedman equation. Does that make sense?
Yeah.
Try to start with the Friedman equation, put um,
Put
put
in r to the negative
put
30.
this in and actually, make it
Establish the variables.
I'm not sure if you actually have to look up the present density. You probably don't because it's probably embedded in you can probably just
Oh,
use
like replacing row knot.
yes. So just leave it as row naught. So right, so the way I did it, and I think I had some intuition about why this would save me headache, is right, I made this specific. So not just row of r is proportional to r to the minus 3, but it's actually
Uh-huh.
row. I should be very careful about my terminology. I'm using the terminology that everybody else uses, but that's not necessarily the best. Um, so I'm going to call this row now,
Now. Nice.
which I mean, it just you should know that the convention is row naught is now,
Interesting.
because like H naught is the
Uh-huh.
Hubble constant today,
Okay.
but it gets confusing when we're trying to talk about time zero
Yeah.
because
We
because
usually
it's
use it
not
as
the
the
zero
initial.
time,
Yeah.
right? So, you know, instead of zero, we should say beginning or something like that. But since the value of R at the beginning is zero, it's tempting to call that zero. So yeah, let's just use nows.
Cool.
Okay. So then that means here's the other piece you're going to need somewhere along here is that, right? Um, let me do this. So we have R dot over R squared is 8 thirds pi g rho, but in this case that's rho now times r to the minus 3, right? So that's our Friedman equation. Um, okay, so and this is also known as h squared, right? The Hubble constant or Hubble parameter.
Uh-huh.
And now if I want to do that for now, then I can say h now squared, which I happen to know is 70 kilometers per second per megaparsec because we've measured it squared.
Mhm.
That's equal to 8
Uh,
thirds pi g
oh, nice. Okay.
rho now times r now, but r now is 1,
Right.
right? So that lets
So
me substitute 8 thirds pi g rho now
70.
in place of 70 kilometers per second per megaparsec
Which
squared.
I guess you could also solve for what row now is
You could.
that too, but it's easier to use
Yeah, and then
70.
you'd have it in exactly. You could that's what I was saying. So but then this will feed directly into when you are trying to when you have this expression somewhere down here. So my kappa squared is 8 thirds pi g rho naught. In fact, so did I just define it? This is kind of cool. That's h, right? That's h naught.
Yeah. Or that's H now.
Or h, that's h now squared. 8 thirds pi g. Yeah, because this is rho now as in our terminology. Yeah.
Nice. Yeah.
So in other words, I defined my kappa is h now.
Yeah. Cool.
I just didn't realize it when I defined it.
You had a good hunch.
I had a good hunch. So
Then
this
it
is h now.
bigger.
So it should be that if I um, if I convert megaparsecs to kilometers, or just look that up, then it should be that I should get an age, t now. Um, Interesting. Okay. Right. So t now, if I did my math right, t now to the 2 thirds is equal to 1 over um, 3 halves h now to the 2 thirds. And if I make all that go to the 3 halves to get rid of these, right,
Mhm.
then I should have that t now
Wait, wasn't the
is
2/3 was also on the three halves, wasn't it? Originally.
you probably are correct because yeah, you're right. Let me fix that. Right. So t now, yeah. So in other words, I can just get rid of the everything's inside of the 2 thirds.
Uh-huh.
So t now is just uh 2 thirds h now to the minus 1
Uh-huh.
if it's matter dominated all the way
Which
back.
is 2 over 210 kilometers per second.
right? And you're gonna have to you're gonna have to convert. I mean, I know this is about right because right, remember in cosmology when we had the age of the universe is approximately one over the Hubble constant,
Uh-huh. Huh.
and the factor in front accounts for whether it's the shape, whether it's radiation dominated or matter dominated or whatever sort of.
Okay.
So you could try you could try the same calculation for radiation dominated case and see what that looks like.
Right, because H is 1 over seconds. So
Yes,
the inverse of H is seconds.
is going to be seconds.
So then when plugging in H, like we know that it's 70 kilometers per second, right?
Right. So you're going to have to do 70 kilometers per second per megaparsec
Oh, right. Okay.
times um, you know, 1 megaparsec
The
is
dimensional amount.
however many kilometers so that you can cancel kilometers and
Got it.
cancel megaparsecs.
Got it. Okay.
And the
Nice.
easiest is probably just going to be, I mean, I've done this calculation before, but you know, the easiest thing is probably going to be just to how many?
Look up how many kilometers are in
Yeah,
a megaparsec.
exactly.
Cool.
So it's 3.1 times 10 to the 19. So this is 3.1 times 10 to the 19.
Kilometers.
So this is going to be 70 divided by 3.1 times 10 to the 19.
That's gonna be,
It's going to be tiny,
yeah,
but that makes sense because
it's 1 over
it's going to be
age.
one over that. It's going to be the age. Two-thirds times one over that
Uh-huh.
is going to be the age of the universe in seconds.
Yeah. Yeah. In seconds.
And then there's what, 3.16 times 10 to the 7 seconds in a year. So then you can convert to years
That's good.
and it will come out to be, I believe, something at least it won't be quite 13.8, but it'll be something around like 10 or 15 billion years.
Wow.
So that's what we mean by the age of the universe. And then I think, I mean, even though we talked through it, I think it'll be really useful to go through like all the steps yourself,
Yeah.
like kind of on your own. But then I think you'll understand the nuances of like what would change that then. Like, what if there was an early time where inflation was happening, and if it was long enough, that'll stretch out that beginning period.
Right.
And so, this will take us back to a certain point, but then but then maybe there was an infinite time before that point, or you start to get
Right.
the sense of the nuance. So I would say, like after you do the calculation, then it's worth looking at Bauman and seeing how he does the details, because I think he probably does, and if he doesn't, we'll find something else that does it.
Cool.
Um,
It's really cool.
All right. So I think that's a good starting point is just to get a really solid handle on what do we mean by the age of the universe? How do we calculate it? How is it different for different domination eras in terms of how, what
Uh-huh.
kind of substances are there? Because, right, because if you try to do this for
Radiation.
if you try to do this for radiation will give you a slightly different number because you'll have R to the is T to the 1/2. But if you do it for vacuum energy dominated, it's going to be a problem. And it's probably worth playing around with that a little bit to see, right? Because then you'll have R dot over R is equal to a constant.
Yeah.
And so you're going to get an exponential behavior. And then when you try to integrate it, there's no there's no zero. Yeah, anyway, that's worth playing around with too. But for now, just try to see if you can get um, if you can get a numerical answer and convince yourself that all the steps are reasonable of just the matter dominated case, I think is a good starting point.
That's good. I
Okay.
think I also want to try and see if I can like I feel like there's a way where we can, instead of assuming that it was matter dominated the whole time,
Uh-huh.
that we can kind of break it up a little bit and have
Yes.
like some radiation dominated and some matter dominated.
Yes, absolutely.
So I want to see if I can do that.
That's a
I
good
think
idea.
that's a rough idea.
Yes. In fact, let me look. In some sense, my my initial question is probably the one to really focus on, which is that um, which is how do you calculate an age of the universe? And I've already steered you in an approximation by
Hmm.
saying, well, let's just assume it's matter dominated, but then can you argue for how you would refine that calculation if it was not always matter dominated, if you include all of the things?
Cool.
Okay?
Yeah.
Because yeah, to actually do the real calculation and get the 13.8 that we get now actually does require doing what you said, which is putting all of the things in there. Um, in which case, interestingly, in which case for our current universe as we know it, then then the 2/3 goes away and it actually becomes really close to one. So it literally just becomes the age is one over H now,
Wow.
because that's where the anyway. So after you play around with it for a while, if you just do if you look for age of the or expansion age of the universe on Wikipedia,
Uh-huh.
it has all of that in there of like all the different factors like you're talking about.
Oh, nice.
All right. That seem like
Wonderful.
does that seem like a good initial thing to sort of play around with,
Yeah. Yeah, most definitely.
and then what I think we should put some version of all of this in our paper just to clarify that when we say t equals 0, we mean an extrapolation to when r was 0
Hmm.
based on these behaviors, and then yeah.
Yeah. Yeah, like maybe not necessarily like go through all the mathematical steps, but like kind of what I did in my presentation about um def like characterizing the eras of the universe with different rows and kind
Yes.
of
Yeah.
giving people that kind of intuition to be able to. Or I guess, yeah, what kind of audience is
Yeah, I mean, we can, I think we can be more, we certainly can be more technical, right? I mean, these papers have, we could certainly put the Friedman equation in there and we could, put some integrals and stuff like that. I'll find out a little more from Dave about the details of the audience, but
Cool.
these can be technical. They're not specifically for cosmologists or something like that, but
Right. Okay. So like these integrals wouldn't be too complicated, but they also wouldn't be too simple.
agreed. Right, right. Yeah. Yeah, I'll send you maybe, well, do the calculation first, and then I'll send you um, this paper about the Big Bang and questioning whether we should even call it the Big Bang or not. I was hesitant to send it to you because I actually sort of don't agree with some of the conclusions of this paper, so I don't want it
Uh,
to be misleading. But it's also nice to know a little bit of what we're trying to explain against or what we're trying to clarify. And
yeah.
and some of these other papers are at least fairly technical. That one in particular doesn't have any equations in it, but um, anyway, yeah, I would for now I wouldn't worry about. I mean, the kind of the level that we talk at would be fine, and the
Okay.
math that we talk about I think would be fine to put in here as long as we explain what we're doing.
Cool. Cool. Okay. And
All
when
right,
when should we meet
you want
next?
to plan another meeting to.
Yeah. So let's see.
How was your visit with your folks? Was it?
It was very nice.
Yeah, awesome.
Yeah, no, it was very good. Um, they came in on Thursday, last Thursday.
Yep.
Um, and then I had like Mandy and Molly came in at like midnight. But I got to have dinner with Mother and Brian at um on Thursday because they came in earlier.
Okay.
Um, and then like Friday, uh, we went to go see Death Becomes Her on Broadway,
Okay.
which was very good. And we went to this incredible Italian restaurant. It's probably the best Italian restaurant I've ever been to.
Wow.
It like everything was so good.
That's cool.
Uh,
And
and then
you had not ever been before. Like,
no,
yeah,
no,
okay.
I had never been before. And then on Valentine's Day, I had work in the afternoon, but in the evening, Kata had work. So we had a reservation at Kata's restaurant on Valentine's Day.
Nice.
Um, and then on Sunday was when we saw Chess. That's like the main reason why they came out because they wanted to see Chess the musical.
Okay.
That's probably the best live performance I've ever experienced.
Okay.
Like it was it was so well thought out. Like every movement, every action, like every single thing that they did had so much intention. And like there was a point to everything and it just made it
Uh-huh.
so great. Uh and then yeah, Monday they went back home. But and unfortunately Sunday evening I started to feel sick.
Yeah.
Hence
Sorry. I think
me
you probably
driving.
have, so you can probably tell I'm getting getting over
Yeah.
something. And it's I think I got it on the plane going to visit my parent. Like I started feeling sick like near the end of my visit
Oh
when I
yeah.
went to visit my folks, and then the plane ride back was horrendous because my
No.
head felt like it was going to explode.
Yeah.
And it was funny because I mean I wore a mask to try to not spread it to anybody else,
Yeah.
but pretty much everybody else on the plane on my way home was coughing or sneezing or something. So it was almost like we all got something on the flight to Chicago, and then we all had it on the flight back from Chicago or something like that. I don't know. So
That's
I,
it.
I heard there's
Uh,
a respiratory flu, like there's a flu variant going around that's pretty, you know, wildly contagious and not quite the same as the flu shots. we're targeting. So I'm guessing that that's what
Huh.
we all have. It could be just a cold too, but
Do you
anyway.
think because I took a COVID and flu test, but it's COVID and then flu A and flu B.
Oh, and it was negative?
Yeah.
Okay, well then it's probably all right. Yeah, because this one, I think it was A. I think it's a variant of
Okay.
A is the one that they said 90% of the flus are. So you might have just your basic,
But I mean,
you know,
it could have been false because when
was
was it
testing
like
for too many things.
no Monday evening, like Monday night, I have a sleep ring and it also records like my temperature.
Uh-huh.
And all night I had 100-degree temperature.
Okay, okay, yeah, yeah.
So
Well,
yeah,
it's funny
no.
because I never, as far as I can tell, I never had a fever with mine,
Uh-huh.
but I have my watch on most of the time that records my heart rate.
Uh-huh.
And because of all my running, my resting heart rate is usually like low 50s, like 52,
Right.
something like that.
Uh-huh.
And there was basically a solid week where my heart rate never went below 60.
Whoa.
Like, so it was basically 10 beats per minute, like very consistently for a solid week, it was 10 beats per minute high. So that was
Wow.
my marker was that, okay, my body is fighting off something because
Uh-huh.
and then as I started feeling better, it was sort of cool. As I started feeling better, then my heart rate went back into the 50s and it's very
Yeah, no. I think last night my ring was like, okay, abnormalities are resolved.
yes.
Like, that's really funny.
Yeah.
It is
Well,
really
and I made the mistake. I mean, it wasn't really a mistake. I would have known better, but a few days after I got back, I mostly felt fine. And so I very cautiously went for a run. Like,
Mhm.
I walked a little and ran a little. And I mean, I didn't push myself at all. But a few hours after I went running, it totally flared back up
Oh,
again. And then it's been like 3 or 4 days more of it's almost like it reset and started recovery over
jeez.
again. So now I'm being very careful not running. Walking seems to be fine.
Yeah.
But anyway, so yeah, take it easy. Make sure that you get fully recovered, for
It's funny
full.
that you say that because I mean today I was like, should I go to the gym or should I go to the cafe? And I decided to go to the cafe.
Yeah, I think that was probably a good call.
But then like tomorrow I was like, I'm gonna go to the gym. Maybe
Yeah,
I
well, I
should
mean,
pack.
it depends. I mean, it depends on what you do. Because walking has been fine,
Right.
but I think just breathing hard and cycling things back through, I
Yeah.
think I just did it maybe a day or two too early. So if I were you, based on my experience, which may not be the same as yours, but I would err on the side of not doing things that require your heart rate to go way up and your breathing to go way up. Because I think I probably just cycled too many things back down into my lungs is
Right.
probably what
Oh,
happened.
it's yeah, because I mean I don't know, like yesterday evening, like around dinner time, like I felt like back to normal. And then like as I was going to sleep, like my throat like was just like swollen like all of a sudden. And then I woke up the next day and like there's just so much congestion. I was like,
Yeah. Okay, that sounds really similar to mine. So I mean, maybe
uh,
I did never take any flu test or anything, so mine might just be a cold too. But whatever, what you described sounds similar to me. It was like I felt almost fine, and then all of a sudden in the middle of the night, it kind of went to my throat.
uh-huh.
So I don't know,
Weird.
but
That's crazy.
drink lots of, you know the routine, right? Drink lots of
Yeah.
water and get lots of rest.
Yeah. I just hope by Friday I'm better. 'Cause working when I'm sick is just the
Yeah,
worst.
yeah,
Because that's what I like Monday evening was like the worst thus far. Like that was the night that I had like a fever of 100 like all night. I worked that evening.
yeah,
So like
yeah.
I was just standing there like my eyes were so watery. I was staring off into space and my head was
Uh,
like pounding. And I was like, this is
that's
horrible.
no fun. Yes, yes.
Yeah. But now like, it's my head's not pounding. Like my head doesn't
Okay,
hurt.
yeah, yeah.
It's just a bunch of congestion.
Yeah, so I bet another day or two and you'll be
Good.
good.
Yeah.
You might want to be cautious about the workout tomorrow though.
Yeah, I don't think I'm going to do it. I think because I'm a bit behind on the cafe, so I'll just use that as an excuse to go to the cafe longer.
Just go for a little walk, a little gentle walk instead or
Yeah.
something.
Yeah.
Calculate the age of the universe
Yeah,
instead.
exactly. Exactly.
All right. Yeah, and try, as you're doing the calculation, try to think of this as like you're building up your own notes of your own scaffolding for all these kinds of
Right.
things, right? So, write it in an organized way that you can follow later and you know what I mean? Like, and that you could change some variables if you
Yeah.
needed to or
Yeah.
whatever, so that it becomes your framework for understanding what it means to calculate an age, even if the actual density values change, right?
Right.
It's like you're trying to get clear on the method, I guess. And then we will go from there to add some other pieces. Then we can maybe next time we can talk about sort of why there's a horizon problem and what that would
Right.
mean.
Okay, cool. Oh yeah, we were trying to
We were
schedule.
trying to schedule it. I know. And I asked you about your parents. So let's see.
Let's see.
You want to
I
do
think
like how much time do you want between?
yeah, generally like I have work like Friday through Monday. Um, so that makes things a bit difficult. But
Yeah. So do you want to do like later next week?
I think could we do like Tuesday um at
Let's see. I've
let's see.
I have a dentist appointment Tuesday afternoon,
Okay.
so I'm probably not available between like I don't know, maybe 1:30 to 4:30 is probably the block of time when either traveling or
EST or PST?
my time,
Okay.
PST. Yeah.
One.
Sorry.
Okay. Okay. So
So I could do morning PST on Tuesday probably.
yeah, I think I'm trying to figure out this stupid consultation is like 15 minutes long. Uh
Well, do you want to just plan or if you're available, like what would be Tuesday morning for me? Do you want to just plan on sometime in that time and then see what
yeah,
it ends up looking like.
could
Or
we
and
maybe
Wednesday, at the moment at least, Wednesday I'm completely open schedule. So if
I
Wednesday
think
works,
generally Wednesdays work, but the next Wednesday I just so happen to have like um a bunch of spontaneous things that I don't usually do.
okay, good.
Um, but could we potentially do like 10 a.m. PST on Tuesday the 24th?
Okay.
And then like I have a like an online therapy consultation um at 11 a.m. PST for like 15 minutes.
Oh yeah, so we
So
could
like
we
if we
could
wanted to go longer than that, like I
yeah,
would just have to leave for like 15 minutes and then come
yeah,
back.
okay. That sounds
Okay,
good.
cool.
Okay, perfect. So we'll plan on 10 and we just put some on the calendar, but we can change it if we need to.
Cool. All
All
right.
right. Good for now.
Yeah, good for now.
Happy physicsing.
Yeah, happy physicsing. Happy early universe physicsing.
Yeah, I think this is going to be really fun. So it will just kind
Yeah.
of just keep building up a scaffold and then just figure out, like as you have questions, we can steer it in new directions based on, like while you're trying to do I'll try to give you pieces manageable pieces that will probably spur new questions, and then we can sort of use those as our anchors. Okay.
I like that.
All right.
All right.
Cool.
Take
Get
care,
better.
Todd. You too.
Yeah. We'll both, by the next time we talk, we should both be have our normal voices back again.
Yes, that sounds
Okay.
good. All
Good
right.
plan. All right. Take care.
Bye.
Yeah. I'll talk to you soon.
Talk soon.